Let me just check one thing. Yes. So, welcome, Onri. So, hello everyone. Mm, wait a second. Just lost. Okay. Yep, there you go. Multiple screen problems. So sorry for that. Yeah. So, hello everyone. Today we have Onri J with us, who is currently an NSF Research Fellow. He has done his doctorate from University of Minnesota, and he has also worked with IBM. Your research is mainly related to hardware, quantum hardware, like spin orbit torque devices, quantum materials, fractal design, quantum computing chips, and many more. And you belong to Navajo tribe, which I found very interesting. And you are the first indigenous American quantum hardware engineer. So proud of you for that. You have very good initiatives regarding quantum hardware. Recently, I discovered your website where you have mentioned many resources related to quantum hardware. So, if anybody is starting with quantum hardware, they can look for your resources and start with quantum hardware because you have many free resources, paid ones. You have described it very well there. So, yeah, with that, I would like you to start your presentation for today. You can present your screen, right?
Yes, it says entire screen. There you go. See something?
Yeah.
Okay, cool. All right. So you can see everything on the screen?
Yes.
Is the PowerPoint showing up?
Yeah, yeah, it's there.
Okay.
It's live.
I'm gonna make sure this thing's not in the way. Okay. Thank you for the introduction and welcome everyone. So today's presentation is going to be focusing on sort of the visualization aspect of these planar transmission lines made out of superconducting materials. And then, well, I have lots of experience with Blender. So you can see here, actually in this little table of contents, that there is a dilution fridge that's been rendered here in Blender. And I I do lots of tutorials on YouTube as well to show how to create these scientific illustrations and sometimes just other figures for fun that are in 3D and play around with the high graphic quality from that. So you can check those out. I'll share some of those things, some details at the end. But basically, we're going to cover some amount of motivation and the background, and then we'll look at some of the figures that highlight the different parts of the quantum stack, and then basically more and more of this visualization aspect for the quantum chip components. And then I'll show you what some of the different kind of amplifiers there are, and the mixers, and maybe some aspect of isolators, mixers, and or should I say isolators and the mixers. They're kind of related, but we'll show some of those images. And these are all open access materials, which is the other aspect of this presentation is being able to show something that's accessible to the public. And yeah, we'll go from there. So basically, when we do consider these quantum devices, there's like, mm, well, this nano. Like if we want to make it into a physical device, we typically have to consider the scale, and the scale of these devices can be measured in the on the order of nanometers. Unless, of course, you're dealing with like single atom control, then, well, you're dealing with atomic scale. But even in the field of nanotechnology, we measure things in terms of like angstroms, which is on the order of like the atomic scale as well. So it's the 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 measurement scale is pretty relevant regardless. And then we're always looking for these desired and undesired effects. And we have all kinds of techniques to build these kind of things and make it possible. And typically it's grouped into two different categories. There's like you can build these things out of metals and insulators, different kinds of insulating materials. And then the other set is like building out of the metals, the insulators, and then some other specialty components or specialty materials that are perhaps semiconducting or otherwise, and so forth. So you can check some of these details out on the nanotechnology National Nanotechnology Initiative. And then here's a little graphic for you, borrowed from this PhD thesis, showing the different wavelengths that correspond to the different, well, say for example, if we wanted to make some kind of really small device, well, we would have to take these different kind of wavelengths into consideration, smaller and smaller. And of course, when you get to like beyond the X-ray kind of wavelengths, then there's also like a lot of safety procedures involved in trying to handle those kind of things. But you know, this is just to show you what that's like. And then on the device, the when we build these devices, they have these transmission lines, these wires that will allow us to send a signal. So we can send this signal and it can propagate in some direction. And we have to consider the magnetic field component as well as the electric field component of those devices. And this is just to kind of set things up. And as a result, we can try to use this as a way to perhaps couple or engineer coupling mechanisms between perhaps one device that's on the chip and another device on the chip. And if we want to couple them together, we have to shape these waveguides and things like that in the context of these different field components. And so, in other words, when we build these devices, we pretty much start off with some bulk structure, and then if we chop it down carefully, or if we grow it, synthesize it in a laboratory, in some like a vacuum chamber, then we can grow these materials and create these quantum wells within these, basically like layers upon layers, atomic layers or nanoscale layers of these materials to turn it into heterostructures and so forth. And then we can do something further. Basically, we're turning it into a wire structure, and we pretty much have all these networks of nanoscale wires on the chips. And if we put some of the couple of nanowires together or next to each other, then we can use them as a waveguide, or we can use it as a way to more or less bend light in some direction. And we can also make quantum dots, which can also in itself, if you have an array of quantum dots, you could to some extent bend light or even emit light from a quantum dot. And so, you know, you end up with things like quantum dot televisions. I don't have pictures of that here, but you can imagine what that's like. And then on the other hand, we kind of have this consideration for noise. We can suppress the noise by using cryogenic equipment. We can basically use this to improve the performance of the device. Could be a single device, it could be multiple arrays of devices that turn into chiplets and so forth. And as a result, we can play around with perhaps the critical currents that's running in the device if it's being controlled or manipulated through a current, an electrical current. But regardless, we have this quantum stack as well. The quantum stack, of course, we there's the quantum algorithms component. It's just you are trying to take this abstraction, you're trying to take this idea that you have in mind, and we keep track of it in the scripts. And then the scripts will be taken down this pipeline, this workflow, all the way down to control electronics. And then these control electronics will have, or control software with the electronics will have perhaps some predefined library with different levels of control. Perhaps, mm, well, it's going to be sent down the pipeline to the device, but the way that is going to take place, I'll show you a little graphic of how that looks like right here. Actually, this is good. So you have some quantum circuit that's just represented by some drawings. You have like a circuit drawing, and if you want to turn that circuit into something that's going to actually control the device, it will basically turn into this shape of an envelope. And that envelope will be applied to this sine wave. The sine wave is basically what's being supplied, and it has to more or less match the frequency, the resonant frequency or operating frequency of some device, a physical device. And eventually that will need to be converted into an analog signal. And but until we get to that point, everything else is pretty much a digital signal, which is well defined by the software and stored in the waveform memory. And then when you mix that together with this is some local oscillator signal that's closer to the qubits or some quantum device, then you can apply it to this mixer. It's a well, I'll show you some pictures of what that mixer looks like. And this mixer will more or less do kind of like it will merge the two signals together. And when these two signals combine, then at the end you'll finally end up with a nice modulated sine wave pulse. And this sine wave pulse will cause the quantum device to rotate, and it will cause it to change its quantum state. And then that's pretty much it. Then we got to take the readout, and then we got to do the same thing, more or less a similar process in the reverse direction, in order to try to figure out what the results are, and then we can compare that, do some benchmarking, and so forth. Anyways, there are all these components inside of something like a, say for example, a superconducting quantum computer. I may or may not be missing maybe one or two items from this list, but the point is we have a bunch of amplifiers in them. We have isolators, circulators, mixers, these converter components. We have interconnects and filters. So it's just this constant step by step conversion. So you're just constantly converting one signal to another, and at the same time trying to keep the noise level really low. And so we would consider this like a quantum limited noise, or quantum limited amplification of noise. And we have to keep everything clean and things like that. But regardless, at the bottom of this entire system, these devices, they pretty much operate on these analog signals. And if you try to excite it with, say, like a square wave, some digital signal, then it's not going to respond very well, or maybe nothing at all. So here's an example. There are some really nice pictures available in this paper from EPJ Quantum Technology. So we have all these interconnects, these wires that will send a signal down to the device, and then we have these filters to kind of help remove any kind of noise that might pick up along the way. And then on the other hand, we have this cryoperm, this little it's a metal tube, and then inside the tube we will put the device, wire it up, place all the connections in place, whether it be like a coaxial cable or maybe some kind of serial cable, or in some other experimental cases like fiber optic connections and things like that. And then when the device is finished being operated on, then we can send it up this amplification chain. And so you can see here there is amplifier components plugged into that mixing chamber, or should I say, inside of this cryoperm. You have this wire that comes out, and then it plugs into the amplifier, and then from there we can send it back up the chain while also trying to keep the noise level really low. And then eventually, the signal still isn't quite strong enough. So we put another amplifier somewhere up here, or even closer to the room temperature, and a little bit closer to room temperature, more relatively speaking, like 3 degrees Kelvin, for example. And that amplifier will will take this already really clean signal, and it will amplify it even further. The thing is, this kind of device, this thing called a hemp, it's mostly based on like semiconducting materials, and it's if you try to bring it down to say like 10 millikelvin, for example, it's not currently gonna have the best performance in terms of trying to keep the noise level low. So that's why we kind of keep it up here, but it's still useful because the gain is pretty high. Anyways, so if we take a closer look, there are the couplers here, and then we have a couple of amplifiers depending on how big of a quantum chip you have. Generally, I'll talk about the TUPA chips, these traveling wave parametric amplifier chips, in a moment. But these chips, let's see here. Yeah, we'll get to it in a moment. But these chips, they typically do have a high bandwidth. I'll show you a little chart of what that bandwidth looks like. They can handle a wide range of signals while also amplifying, providing this noiseless quantum limited amplification. And then, of course, we can plug in a bunch of perhaps isolators to redirect the signal if we need to, or end the signal. And then, let's see, what else can I talk about here? We have some level of filtration available here if needed, and that's it. Okay, so on the other hand, I was talking about if you have like some smaller chip, like depending on the size of the chip, you might have perhaps like a single cavity with the chip inside of it, and then you might have some coaxial cables plugged into it. And typically this would not have too many quantum devices on it. You just want to do some testing, then this is fine. And then some other systems might have a larger set of cavities, and then inside of this device, it's more or less a straightforward way of using a cavity, utilizing a cavity to actually read out a device. And then in this case, if you use either one of these kind of cavities, for example, then you don't necessarily, I mean, this is behaving as a resonator. And in that case, you don't have to design extra wire components that will resonate on the device. So these are just some extra options available. And then here's a picture of what that circulator looks like. So there is a signal. It's like typically there are 3 ports on it, and what this device does is it's just behaving like a roundabout. And this roundabout will take place as a matter of this microwave interaction, or should I say this disk, the microwave signal or RF signal is going to flow through this. It's going to flow throughout this disk, propagate on the disk, and then when this magnetic field is provided by some ferrite disk, then it will penetrate through this plate, and it will bend the signal in one direction or another. So if it bends the signal this way, what that means is if you plug in a cable here, whatever signal you send in here will always go in this direction. And if you send perhaps a signal into this port, it will only go in this direction and it'll never go in that direction. So there's this interesting relation. We can actually show perhaps let me show. Okay, yeah, this is a picture of what like a side view of the magnets, and then there's a plate here where that signal will propagate on, and this is actually just a nice open access paper showing what the simulation result looks like. You put a magnet there and we'll bend it in this direction, and that's one way of visualizing it. So you can do the same thing with this one. This one does not have necessarily a transmission line. It's more like a square pipe of sorts. That's another way to do it. We can do the same thing here. This is just more pictures of what that device looks like. So these are kind of like parts of the quantum system that more like they operate on a larger scale. You can hold these components in your hand, and that's about it. They operate very similar to similar room temperature components used for like radio frequency control, like on say for example, you wanted to do you have your own radio station at home. That's one way to do it. But anyways, if you go down to the chip level, then some of the common planar transmission lines will have microstrips on them. We will have slot lines, which are less common, and then the very popular coplanar waveguide geometry. So there are some properties that associate with each of these different kinds of geometries and the different kinds of perhaps like fabrication complexity that we have to consider, the crosstalk, among other things. And then we also have to consider how is this kind of geometry going to perform at higher frequencies versus lower frequencies. So you can have a look at this chart here. Okay. Anyways, we'll get back to the drawings. So this is something I found very interesting. This geometry, it looks very simple here on the right. So like we could actually highlight how simple this geometry looks like. There is a transmission line right here, and it has a shorted end, and it also has an open end, and then there's a ground plane here. There's another transmission line on this side, and you can have a port coming in and then a port going out, or vice versa. And if you look at the lump element equivalent, the circuit drawing of that, this transmission line is being counted as an inductor. And then whatever gaps exist, wherever there's no metal on this circuit, which is this white line here, or this yellow line here, this gap is behaving as a capacitor. So this capacitor exists, this capacitance exists right here between that transmission line, and it kind of jumps over to this, it shares somewhat of a capacitance with this other capacitive element here. So you can see that happening here. Capacitance CC. And then on the other hand, you have another inductor, which I just mentioned, and there is a capacitance around this inductive element as well. And that's, I mean, the whole point of this is that if you send a signal down here, then this coupling mechanism will allow this transmission line, say for example, if this was a resonator, it will actually feed off of that, whichever resonant frequency is coming down this transmission line. So if you were to sweep a signal from one frequency to some other frequency, then whatever the resonant frequency of this, say if this was a resonator, let's say, for example, this had like a resonant frequency of 5.5 gigahertz. Then if you send a signal down here at 5.5 gigahertz, then this will actually start to resonate. If a signal coming down this transmission line was, say, for example, 6 gigahertz, then this resonator will not resonate. There are some nice videos you can check out of how different objects respond to resonant frequencies and so forth. So just wanted to point this out. This is one of the things that I call the beauty of the abstractions in these superconducting circuits. And you can see some of those components here, they look kind of like elbows on the chip. And so you can kind of guess what the direction is, what the direction is flowing on this transmission line. In this case, it would be flowing to the right. Okay, and then here's another example of visualizing that how that signal is being sent. This is an example from COMSOL. There is a resonator here, and then you have this transmission line here. This transmission line, I believe another term they have for it is called a feed. It's like a feed line. There's another term they have for this. But what this resonator is doing, if I could, oh yeah, there's no drawing tool on here, I don't think. But the signal would send from port 1, and then it will feed off of this, or should I say this resonator here on the right would feed off of that signal, and then it will hit this open end of the resonator. And because it's open-ended, it will actually resonate with a much greater eigenfrequency. And you can kind of see that high peak here in this visualization. And then what will happen is, once that resonance hits here, that signal will travel down this transmission line all the way to the end, up to the shorted end. And then the shorted end will not resonate. It will not resonate as much. The eigenfrequency will not be as high, but it will bounce back and will reflect, and it'll come this way. And then this transmission line will pick up that signal, and then you can measure what this resonator is doing. So this kind of brings us to another slide, which is about the amplifiers. So actually, here's one more example. It's just you have the ground plane here, a ground plane here, and then you have this center transmission line. So the transmission line is being considered, or is being counted as an inductive element. And then you have this capacitive element as well, which is just a gap. And then, well, the ground is the ground plane. And this letter N is just to represent that this is the nth cell. This is one cell. So anyways, here's a nice drawing of, or more like a animation I made to go along with this drawing of what this parametric amplifier is doing. So this device is considered to be a transmissive mode device. It's forcing or merging these signals together. It's mixing these signals together. You're trying to amplify some weak signal, like a microwave signal, coming from a device. And then what it will do is it will do its best by using this linear array or series of Josephson junctions. And then it will force these two signals to mix together. And then at the very end, you end up with an amplified signal right here. So you have this weak signal here, then amplified signal. And then there are some other secondary signals that will also come out as well, but those are not the ones that you want to focus on. And so this is the circuit drawing of what that device looks like. So typically in this kind of amplifier, you would have about maybe three different cells in series. And then at the ends, it's connected to this this resonating element. So here we go. And then here's another amplifier. This is what you call a kinetic inductance amplifier. This device does not have a Josephson junction in it. There's none. These are all just in inductive connections all together. We also call this a fishbone geometry or fishbone tupa, fishbone traveling wave parametric amplifier. And in this device, this whole thing is just superconducting material, superconducting thin film. And then if you were to look at it as is, I guess you could try to guess what the capacitance is, or try to estimate what the capacitance is on this device, and then maybe the inductance as well. But in this case, you might not know without the circuit drawing which part, like how many. If we were to draw like a circuit equivalent, what part is which. So in this case, you can see here that this gap right here is being considered as this one capacitive element. And then you have this one inductive element here. So you have one bar, and then this gap, and then the ground plane. So it's almost like having one cell here. And then from this subcell or cell to this cell, or in between these two different cells, there is another inductive element here, and so forth. And so this would continue on all the way to the end of the device. And then you can experiment or provide a simulation of what this amplification would look like, perhaps using something like Julia. Is a Julia Josephson circuits library that's available. You could probably try this on there. Okay. And then here's another common one, another common amplifier. This amplifier, I also rendered this in Blender, but this amplifier, what it's doing is basically the same thing. You're taking some very weak signal, and there is a pump signal that's fed from this side of the device. I didn't write it down here, actually. I just realized that. But there is no, this is not a transmissive device. This is a reflective device. It will send a signal, you will send a signal down this resonator element, and then there is a set of Josephson junctions, or a pair of Josephson junctions over here to make a squid. And then this squid is coupled together with this inductive element on this side. So in other words, there's a pad on this side of the device, and you could wire bond a connection here, and then that will send this inductive pump, what am I saying? The pump signal will travel down this inductive element, and it will stay in this region. And this DC squid will feed off of that the energy from the pump, and then it will reflect back up this resonator, back out this to this side of the device, of this amplifier chip. And then you have an amplified signal. So now you can see the original weak signal, and then you have the final output, the final amplified signal with minimum noise, or no noise, noiseless, we should say. And that's what's happening on this device. But the trade-off here is that because you're dealing with only, say, for example, one set of Josephson junctions, or one particular resonator length here, in this kind of device, the bandwidth is limited. Among other trade-offs, I'll show you what the table looks like to kind of summarize this. And then there are other designs similar to this kinetic inductance traveling wave amplifier. There's also this other one called a nano bridge kinetic inductance amplifier. This also does not have Josephson junctions in it either. They're just simply, well, it's shunted or short-circuited from this capacitor pad to this other capacitor pad. There is just one 20 nanometer wire that is short circuiting between these two. And by means of this kinetic inductance, you will send a signal down these pads. It will couple here to this capacitive coupler pad to kind of smooth things out. And then it will meet at this inductive wire, and then it will send, it will reflect, it will send a signal back out to those pads. And then you can amplify a signal. And so it's reflective. So reflective, transmissive, reflective. And then traveling wave amplifier, the initial one that we showed, that one is also transmissive. There's no reflection necessarily happening on those kind of devices. And then here is a nice table to show you what those different amplifiers are doing. So basically, if you want to focus on some large-scale quantum system, for example, you're going to need something that's going to handle the higher bandwidth. And so, in that case, what you want to look for is something that's more traveling wave based, because the traveling wave based parametric amplifiers can handle the much higher bandwidth. They can handle a wider range of frequencies. And then some of the newer ones, like kinetic in Kippa, or the nanobridge kinetic inductance amplifier that we were looking at, this device does not have much of a bandwidth, that high of a bandwidth. You can see here it's only like a few megahertz compared to the gigahertz range of bandwidth that these other traveling wave amplifiers can achieve. And so you can basically use this table as a guide for picking what kind of amplification. Well, somewhat of a guide. I could only find so much information about these different amplifiers. The more common ones, like the JPA and the JTUPA, there's so much information available on it, so it's more readily available. But some of the newer ones and some of the more pretty much just the newer ones, is not every detail is provided. For example, the pump frequency is not provided for this QCPA, which is what we call a quantum capacitance parametric amplifier. I can show you some pictures of what this device looks like sometime in a different presentation. But anyways, and then now if we start to look at the devices that are not for amplification, but rather used for, say, for example, qubits, we can look at this diagram. There's an inductive element here. There is the Josephson junction, and then there is a capacitive element. So the inductive element is being highlighted as this orange colored geometry. And then the green colored geometry, this is the capacitive element. And then the Josephson junction element is right here where this red, actually no, it's at the end of this wire here. So that's where the Josephson junction element is. And I believe this device is based on a flux, what we call a flux qubit. And then here's another drawing. So it gets increasingly more complex. I'll show you some of the more complex designs. So this design, it's using the color code as a way to try to help you identify what's happening on this device. There are inductive elements here and here. So this sort of dark blue color is on the left side. And then there's a Josephson junction here, which is in pink. Oh, if I just realized I could use a laser pointer. There's a pink Josephson junction here on the left side. And there's another Josephson junction on the right side, colored in green or greenish yellow color. It's behind this label. It says 30 microns. This is just a scale bar. It's behind a scale bar. And then there is another junction here, I believe this junction is being labeled as a. It's sort of like a junction that's designed to couple these two sides of the device together. And then there's another inductive element here, and then the capacitance is simply just measured as the gap in between these two inductive elements. So basically, everything you see here that's in gray, that's all just it's all etched out. There's no metal that's been deposited on either sides of these inductive elements. So there you go. And then there's another capacitive element here that's also being considered to be this whatever this gap is in this geometry here and also here. So if you can account for these elements on the device, then you may get a better picture of how to simulate or how to perform the analysis on such a device. And then here's one that's a little more complicated. So this device is also got a actually no, this is the same device. This device has a circuit element here, or at least it's from the same paper, I believe. Let's see here. Similar kind of work, but you have one side of the circuit that's got a bunch of control, like X, Y, and Z control here. And then as you go further up, you start to get to these other capacitive elements here. Let me see here. I need to zoom in. There is something I wanted to show you here, which is a wire. Okay, where is that wire? This is okay. This is not the wire that I was looking for. There was another one I wanted to show you, but basically there is an antenna on either side of this device, and just by means of having a close proximity and this gap here, as long as there is a gap, we can consider this to be a capacitive element. And so that's how the coupling is going to happen. It's going to feed off. It's going to feed off of this antenna, and then the signal will travel, and it will go up into this resonator here, and then it will also travel in this direction, and it will couple together with this particular circuit that has inductors on it, and it's got capacitors. So it's just a bunch of inductors and capacitors connected together, and then another coupler in between, and then the other set of inductor capacitor elements here on the left side. So this is just an example. Okay, so now if we look at something more common, like the transmon quantum chip, there is this transmission line, the feed line. Here, there are two sets of them. They're wire bonded to a package. And then the readout here you can see is coupled. All right, let me use I could have sworn it was a laser pointer. Where's the laser pointer? Yes. So you can see here the feed line. Yeah, the laser pointer is gone. The feed line is being dominated by this inductive sort of elbow. So this elbow is going to feed off of this transmission line, and then it will send it to this capacitive element, which is connected to the Josephson junctions here. And then whatever that signal is, actually no, this is the readout resonator. So the signal will send out this way to the device. It will go to this cavity, and then that capacitance will couple to the device. And then since the transmon here is a reflective device, it's going to send it in this direction, and it will go down to this resonator, and then it will send a signal out to this transmission line, and then you can read it out from here. So, of course, each of these resonators is a different length. These would have to be at different resonant frequencies. So the resonant frequency will allow you to differentiate between which device is which. And this is just a little closer look at the device here. This is the capacitor, and then you have a Josephson junction that's been deposited on this capacitor pad. So it's a bit magical. All right, so if I move on, where's my... And same thing here. There is a Josephson junction here, and then there's a capacitive element. But since this device is being placed inside of a resonator cavity, this does not require a resonator wire to be connected to it. So in this case, it's probably one of the most simple experimental setups you can have for measuring a single Josephson junction used as a transmon. A squid. So if you made this into a squid and you want to do some experiments on this device, then it's a very simple setup. You just put it in a cavity, plug in the wires, and then run the measurement. Of course, with the context of knowing what the resonant frequency of this device is. But you can find that out. Okay, and then if you want to do it outside of some microwave cavity like this, then of course you can attach a resonator to it, some resonator line, and then this coupling, you can couple this resonator together with the device by simply adding a gap. So this one is actually not using an inductor to couple these two together, but instead it's just using capacitive elements to couple the transmon device here with the resonator line. And then there's a little bit closer look here on the right side. They call this feed line an antenna, this transmission line, an antenna. And then there are some squid devices here. And then these squid devices are more or less deposited all together on this part of the device. Or is it actually here? I believe it's on the left. These are just some examples. Okay, and then one more example before we get to the end of the presentation. But basically, in this case, we have some RF input, and then the coplanar waveguide sends a signal down here to the device, and then it's using this capacitive coupling to send a signal, and then the signal will reach the Josephson junctions here, the squid elements, and then when the device sends or reflects the signal back, then you can read it out back through the same resonator line. And then this resonator here, this line you can see here will actually feed off of that as well. So we can actually draw something like this as well in K layout, and then what you can do is try to simulate this in an FEM program or some other qubit analysis tool. And then, of course, if you want to try to play around with perhaps if this is done with tunable coupling, for example, or tunable, if this is a tunable quantum bit, tunable qubits, then we can apply a flux bias as well to this device to more or less shift the frequency on the device, among other things. So that's about it. And then this is just to show you this is how we make the devices. We can do like electron beam based lithography to make some tunneling devices. This is related to the tri-layer process. And then we can also make them using other processes that are based off of like projection lithography. That's also possible, or laser lithography. If you want to make micron scale structures, those are also possible. But for the devices that are nanoscale, like the individual Josephson junctions, we can use a similar process that we're showing here. And then this is kind of what it looks like. We can actually we can design them in Qiskit. We can actually lay them out, clean the layers up, and then we can put it inside of a lithography machine and then pattern it. So this is all documented in some of my repositories on how to make these kind of devices and pattern them. And then this is one of the repositories that you can use for reference. And this is actually the final slide showing what this documentation looks like. There's so many components you can look at, lots of pictures, lots of tables as well. So with that, I conclude my presentation. Thank you.
Thank you very much for the presentation. It was wonderful presentation. I think this was like my first ever very focused session where I was seeing those hardwares and those chips. My master's thesis is related to this, but it is a theoretical one. But yours is like
Okay.
total hardware experimental work. Seemed very interesting.
Yeah. I've just been working on hardware this whole time, and actually in one of the presentations, I mean not presentation, one of the documentations I put together, I have a nice comparison between like a quantum system setup versus something like audio control. Because when you build audio amplifiers, they have all of these analog signals that you need to calibrate, or you need to try to match it with a speaker. These are all, they require an analog signal for the most part. And we can also do it through a vacuum tube, because a vacuum tube can put a really nice analog signal, a pure sine wave. And so I compare it with that, because some of those kind of components, they're easily accessible, like around the home. Audio amplifiers are not too hard to find. And so you will find actually a lot of things like that in a real quantum system. And it kind of helps you get up to speed as well to learn about the hardware.
Yeah. So thank you for the talk today. It was wonderful.
Yeah, no problem.
So
all right. So it seems like we're on time today. With the scheduling. Yeah, that's good. All right. So is this the end? Finished?
Yeah.
Okay. So, well, until next time, I guess.
Yeah.
All right.
Bye
Well,
bye.
I will sign off now.
Yeah.
Cheerio.